stretching our understanding of quantum limits and seeing how theory shapes real technology. We are honored to have Professor Arun Pati speaking on quantum speed limits and quantum computing, followed by Nathan Ernst Nobel, who will walk us through software tools for quantum advantage. Two powerhouse talks, two perspectives, one is academic and another one industry, both pushing us toward a future where quantum isn't just research, it's reality. So settle in, stay curious, and let's get day 3 started. For the first talk, we have Professor Arun K. Patti. Professor Arun has made many pioneering contributions in the area of quantum computation and quantum information. He has been working in the area of quantum science, quantum computing, and quantum information over last 35 years. His seminal contributions include the no deletion theorem, no hiding theorem, no masking theorem, remote state preparation, and stronger uncertainty relations. His research papers have been featured in Nature, Science, Scientific American, and Nature Asia. For his original and creative contributions, he has received many awards. This include the Indian Physical Society Award for Young Scientists, Kolkata in 1996, Indian Physics Association Awards for Best Scientist of the Mumbai in 2000, Samanta Chandra Shekhar Award for the year 2009 from the Orissa Science Academy, India, and the Distinguished Alumni Award from Berhampur University, Orissa. He is an elected fellow of the Indian Academy of Science, Bangalore, and also the fellow of the National Academy of Science, Allahabad. He was a J.C. Bose National Fellow in 2019. He consistently ranks in top 2% scientists in the world by the Stanford University. He also figures in the number 1 position as world's famous quantum information scientist. So let's virtually welcome Professor Arun.
Thank you very much, Davarti, for your kind introduction. And thanks for inviting to this event. So, can you see the slide?
Yes, it's visible.
Okay. So, I'm going to talk about quantum speed limits and their applications in quantum computing. Quantum speed limit has been there. I mean, it is already, we know this for almost the last 80 years, since 1945. But
Bro, it comes if you deny.
Bro, actually, they are actually allowing me to.
Hello? Are you saying something to me?
No, actually, it's a participant seat, so we muted him.
Okay. So this notion was already there since 1945, but over the last 10 to 15 years or so, this has been an active area of research, and a lot of groups are working on quantum speed limits, trying to generalize this in various directions, and trying to apply in quantum computing, quantum control, quantum thermodynamics, quantum battery, and many other directions. So I will try to give a basic kind of overview of this notion about quantum speed limit, and then I will try to see how we can apply in quantum battery and try to estimate, like, run algorithm, estimate time in quantum computing algorithm and its use. Okay, so there are two things we'll try to highlight. Okay, so here is my outline. With a brief introduction, I will try to tell the original quantum speed limit, and then I will try to tell you about something we have done over the last 2 or 3 years about something called stronger quantum speed limit, and then I will talk about quantum speed limit for observables, and then applications in quantum computing, and try to summarize finally. Okay, so in quantum mechanics, we know, I mean, this theory has been very successful. One of the most remarkable discoveries of human mind, but quantum physics also has several limitations, which could be either operational or could be dynamical in nature. Okay, from dynamical point of view, you have the quantum speed limit, and that has played a pivotal role in quantum computation, quantum control, as I said, also even quantum thermodynamics. And these limitations are not just theoretical curiosity, but also they have practical relevance. As recent years have already witnessed the rapidly developing quantum technologies. So this is the thing, and this is the notion that has a lot of applications. Okay, so what exactly is quantum field limit? So very simple question. So all of you know that whenever you deal with a quantum system, it satisfies Schrodinger equation. Okay, so all of you know from your BSc or from your college level. So in an abstract setting, you can write this Schrodinger equation as IH by d psi by dt equal to S acting on psi of t. Okay, so this is your Schrodinger equation, and what you want to know is you start your system initially in some state size 0, and you want to reach a state after some time t, which you denote as psi of t. Okay, so you will evolve the system by applying some unitary operator or by applying some Hamiltonian, and on the quantum state space, the system may travel along some path which I denote as actual path. Okay. So the question you want to address is how fast you can evolve the system from initial state to final state. Okay. So what the time it takes in going from initial state size 0 to the final state at time t? Okay, very simple question. And because of its simplicity, it has a lot of applications in a variety of contexts. Okay, so as you can see, given any arbitrary path connecting to endpoints psi 0 psi t, you can always find a shortest path, which is depicted here as like the dotted line. Okay, so naturally you would imagine that if you could drive your system along the shortest path, you will reach on a certain time scale. Okay, that is very natural to to think of. But then, hello, hello.
Sorry,
Any
sir, we
question?
are actually no. Actually, it was not a question. Actually, a participant, we muted him.
Okay, so given an arbitrary Hamiltonian, a priori it is not very clear that you can actually travel along the shortest path. Okay, if you could find an Hamiltonian, which often is known as optimal Hamiltonian, then that may drive the system along the shortest path. But often it is not the case. So that is the reason you like to put a bound on the time. Okay, how much time system will take from going from initial state to final state. Okay, that is essentially to do with quantum field limit. Okay, so quantum field limit in short QSL defines or it defined as the maximal dynamical evolution speed of a quantum system, and it can determine the minimal dynamical evolution time required for a quantum system to evolve from initial state to final state or target state. Okay, as I said already. Okay, so over last several years, we see the importance of quantum field limit in variety of contexts, starting from, as I said, computing to quantum control to quantum thermodynamics, quantum battery, and many more things. So quantum field limit QSL helps to determine the minimum time required for a quantum algorithm to evolve from initial state to final state, ensuring efficient execution. As I said, this question is so simple that you can imagine in any practical scenario. Like in quantum computing, what do you do? Okay, you prepare your quantum computer initially all qubit instead 0, 0, 0. And then you keep on applying sequence of unitary operator depending on the algorithm you want to implement. Then you want to reach a final state, and from final state you will read out the answer. Okay, so in a simple setting, quantum computation is nothing but evolving your initial state of quantum computer to a final state. Okay, so again, if you want to execute your quantum algorithm in the shortest possible time, then you have to know the answer, how much time system takes or quantum computer takes in going from initial state to final state. Okay. Similarly, in quantum gate operations, you can use QSL, and that can help to define the shortest possible time for implementing high fidelity quantum gates. And you can also design optimal quantum control protocol by setting the limits on the speed of the state evolution under external driving forces. In quantum thermodynamics, QSL provides bounds on how quickly energy or information can flow in quantum systems, influencing the efficiency of quantum heat engines. Okay, so to understand the notion of quantum speed limit or QSL, we have to bring some notion about geometric aspects of quantum evolution. Okay, so we know that a quantum state lives in Hilbert space, but then because of the state normalization and the overall phase do not matter, essentially the quantum state space, nothing but technically it is called a projective Hilbert space or the space of density operators. And when a system evolves in time, it traces a path on the projective Hilbert space. Okay, so those who are a little bit familiar with quantum computing, courses, for a single qubit, your projective Hilbert space is nothing but your Bloch sphere. Your projective on the surface of the Bloch sphere. So your surface of the Bloch sphere essentially is the space on which your quantum states move along. Okay. Now you can ask the question, starting from some initial state to final state, if you want to reach how much distance quantum state has to travel. Okay, and you can prove that the total distance that system takes during time evolution, basically governed by up to some scale factor like 2 over h bar. It is basically given by integral of the fluctuation in the Hamiltonian. Okay, what do you mean by fluctuation? I will come to that. So fluctuation basically your variance of the Hamiltonian in the state psi. Okay, and the speed of quantum evolution is governed by the fluctuation in the Hamiltonian. Okay, so how do you understand that? To understand that, you have to bring the notion of distance and quantum state space. So basically, what you do is you take the definition of quantum distance. Given any two states, psi1, psi2, you can define a distance. Basically, 4 into 1 minus psi1, psi2 overlap and mod square. That is distance. Now, if you take two nearby states like psi1 at time t and psi2 at time t plus dt, then you can have the infinitesimal distance as you see here. And then what to do is you use Schrodinger equation and do the Taylor expansion of the second order here, and then simplify a little bit. Then you will see that this ds basically twice delta h by h bar times dt. Okay. Then you can define a speed which is ds by dt, that is twice delta h by h bar. So you see a very simple and beautiful quantity appears here, and that determines the speed of quantum evolution. Okay. So fluctuation in the Hamiltonian has acquired a new meaning in the context of geometry of quantum evolution, in the sense that not only it has the traditional meaning of variance, but it also decides the speed of quantum evolution. Okay, and then you can also define total distance. Basically, if you integrate this quantity, you get the total distance. Okay, this was shown by Anand Harnov in 1990. I also did something in 1991, trying to define a distance using a different kind of metric. Okay, so quantum speed limit has to do with the fact that the total distance traveled by a quantum state during time evolution from 0 to t is always greater than or equal to the shortest distance. Okay, so s, if you denote the shortest distance as s naught, okay, then you can use the inequality that is s is greater than or equal to s naught. Okay, so if you remember the picture that I showed a little before, okay, so you can appreciate this from where it is coming. Okay, from there, if you use that this is greater than or equal to s naught, then for time independent Hamiltonian, this will come out from the integral. You will have basically twice delta h t by h bar is greater than s naught. From there, you get this bound. Okay, so t is greater than h bar s naught by twice delta h. This was proved by Mandelstrom and Tom in 1945, almost 80 years back. Okay. And how to define S naught? S naught basically you take the overlap of the initial final state. That is basically cos of S naught by 2. This is some kind of angle, okay, angle between vector psi 0 psi t, and that is the shortest path, okay. Many years later, in 1998, Magnus Levitin, they found that they found different kind of bound, which is basically trying to prove that the T is bounded by h bar s naught by average of the Hamiltonian, not the variance, okay. But I will not be talking about this bound, so I will mostly focus on this bound, okay. And then Levitin and Toffoli, the same person Toffoli, which you may be familiar, the Toffoli gate, 3-qubit gate, the same person Toffoli. So they proved that if you take this together and put a maximization over this, so either this or that, there is a kind of unified bound and that is tight, okay. So if you want to know how to derive this bound, you can do in two distinct methods. One method is the geometric approach that already I told you, okay, and that was done by Anandan Harnov and myself in 1991. That is basically what I just told. The total distance is greater than or equal to shortest distance. But then you can also use Robertson uncertainty relation and prove the same thing, okay? And this is exactly what was done by MT in 1945. Okay, so coming to MT bound, we know that MT bound can be achieved and saturated by optimal Hamiltonian. That is, if you can find a Hamiltonian which will drive the system along the shortest path, then of course you will have the equality sign. And this typically occurs when the system is in pure state and Hamiltonian time independent. But for non-optimal Hamiltonian, MT bound is typically very loose. You know, I will show you. I will give you some example where you will see how loose this bound is. And as a result, the natural question comes to mind is it possible to derive a stronger bound, a stronger version of MT bound that is more tight than the original MT bound, okay, or non-optimal Hamiltonian. Okay, so before I go there, I just want to, focus here that quantum speed limit has a lot of applications in quantum computing, quantum control, quantum battery, and quantum thermodynamics. And in my talk, I will try to focus only these two things: quantum battery and quantum computing thing. I will not have time to, go into detail of this and these topics. Okay, so already, in the literature, we have seen some application of quantum speed limit in quantum computing. Because the original formulation of QSL by Mandelstam and Tam, they designed this for quantum evolution between orthogonal state, okay? And that itself naturally falls under computational setting, because if you want to go from some initial state to final state which is orthogonality, like, you can imagine like you're going from 0 to 1, like a NOT gate, so you can ask the question how much time you take for system to implement a NOT gate, okay? And Magnus Levitin, they also make a slight difference to interpret the result in the context of number of gate operation that a computing machine can achieve per second. And Setlard in 2000, he also used this QSL in the form of energy time uncertainty relation in the context of computational limitation of the universe, okay? And myself and my collaborator in 2009, we tried to estimate this runtime of quantum algorithm using this QSL. Okay, so before I talk about this topic, so I will talk about stronger quantum speed limit. To understand that, we have to use the notion about stronger uncertainty relation that we proved in 2014. So myself and Nekone, we had this relation that given any two observable A and B, you can write this as delta P greater than something like this plus some additional piece. Okay. So if you drop this, what you have is basically your Robertson relation. So that is quite well known, but because of this additional thing, this is much stronger than the Robertson Schrodinger relation. Okay. Now, how to derive the strongest quantum speed limit? So what you do is you choose a rule B to be Hamiltonian of the system, and then use equation of motion for the observable A that already you're familiar. Okay. So IH d by dt of average is basically A and H commutator, and it's average. Okay. Now in this relation, you choose A and B suitably. Okay, so you choose B to be Hamiltonian and A to be a projector. Okay, if you do that, then this looks like this. Okay, and I put everything under this short notation. So the extra term that you see here is basically R of t. Okay, R is a function of t. Now, if you choose A to be projected onto initial state, then we know that because this is projected, this will satisfy this S square is same as A, and variance in A is basically you can find out that looks like half sine S naught. And what is average? Average basically psi 0 psi t. That is basically your cos S naught by 2. Okay. And then if you will algebra, you will see that you can express the bound something like this. And from here, if you integrate both this side with the bound, which looks like t greater than h bar s naught by 2 a delta h plus integral of this quantity. Okay. And this quantity is telling you something interesting because if you drop this quantity, you have the original empty bound. Okay. And because this is real and positive, you get an additional piece, and that makes it more stronger. Okay. And that is why this is called stronger quantum speed limit. And not only that, we could also prove that if you have an evolution along a shortest path, then this extra term vanishes identically, which means you get back the empty bound in equality form. Okay, we should be there, and we should be satisfied per consistency. Okay, and that exactly happens. Okay. So now I will tell you two simple example. Not two, just one example, but with two different settings. Okay, consider non-iterating quantum systems with m subsystems. Okay, all initially state psi 0 psi 0. Okay, are all identical, and each of the psi 0 is equal superposition of orthonormal basis state like this, and n is the dimension of the each subsystem. Okay, and as I said, they're not interacting, so you can choose your Hamiltonian, local Hamiltonian for each subsystem, and then total Hamiltonian basically sum over all HI. And each HI is something like this. Okay. And this is a homogeneous energy system with every subsystem having energy average given by this quantity. Okay, as for omega m into n minus 1 by 2. Just remember that m is the number of subsystem and n is the number of, the dimension of the each subsystem. Okay. Then you can find the average, you can find the fluctuation, and you can also find analytically, you can find also the transition amplitude because it is exactly solvable. So that looks like this, and you can also find the transition probability. From here, you can find what is actually S naught. Okay, so once you do everything, then you can plot this new bound compared to the old bound. Okay, so let's do that. So you do the following: you divide T by 2 T SQSL stronger limit, and you divide T by T QSL due to empty bound. Okay, so this is the ideal line. Okay, if your bound is good, you should be close to this ideal line. Okay.
So sorry for the interruption. There are some questions if you want to take them right now.
Sure, yeah.
So there's a question says that what is the actual physical phenomena that causes Hamiltonian interference?
No, Hamiltonian don't interfere. System state can interfere, right? You see the quantum interference due to superposition principle. Okay. So if you superpose two quantum states which are not orthogonal, you will see the interference. Maybe the question is not properly phrased. I don't know. So
There's another question. When do the two bounds become equal? And in what situation is one tighter than the other?
yeah, I already told that, right? If you see here, okay, if you see here, for general Hamiltonian, this bound will be tighter because this is always real and positive. Okay, so you have something plus something. Okay, because of this something which is positive and real, this gives a stronger bound. Number one. Number two, if you move your system along the shortest path, then the both bound will be equal because this will be 0 and this equality will hold. Okay, so then in that case, new bound and the Mendelssohn term bound both will be equal. Okay, does it answer your question? Is it clear?
Yeah, yes, it seems for the chat.
Okay.
And one question is how should we proceed to prepare a quantum circuit for state preparation such that it takes an efficient path, short time, least circuit depth?
That is the that is one of the biggest question. So I mean, given some particular algorithm you want to implement, a priori there is no prescribed rule or instruction that if you prepare in this way, if you follow this circuit, you will be able to efficiently reach that. Okay, that is the goal of so-called low depth circuit design, right? So it's not always very clear, not very easy. But what can happen is QSL quantum field limit can give an estimate, kind of benchmarking whether your design is efficient or inefficient. Because if you could design your suppose you have say 10 different designs, okay, and you estimate your QSL for all such a design and just find out, okay, this takes less time, then maybe you can say, okay, this is the best design, okay, that you can say. But apparently there is no clear rule how to achieve that. That is one of the difficult. I mean, difficult means one of the research topic. Okay. Should I move?
Yes, so one more question is that when we determine quantum speed limit, is it determined on the basis of the hardware system we have?
Not. I mean, not really. That will contribute additional things, but speed limit is basically governed by the initial state and target state and what Hamiltonian you are using to drive the system, because that will ultimately decide the speed, right? So, but hardware design will come into play in the sense that if you have to estimate total runtime for a particular algorithm, so what will happen is it is not just the time due to state evolution, but maybe there is some noise, maybe there is some additional post processing or something. or maybe some waiting time, and also that if you count everything, that will add up to the total execution time. So hardware inefficiency will play a role, not directly but indirectly, I would say. Yeah. Okay. So any other question or?
No, sir. No questions as for now.
Okay. Okay. So here what I want to show you is how tight this bound really is, So very simple example, no complication, nothing, no interaction. So simple M body system, M subsystems with the non-interaction. Okay. So what you do the following: you divide your T by T stronger QSL and T by T QSL due to empty bound. So ideally, uh, as you can, for the obvious for you that ideally this is the line. Okay, but if your bound is really good, that should be very close to the ideal line, right? Now, how to do it? You in this case, you fix the number of subsystem as n equal to 2 and change the dimension. So n equal to 8 and 14. So you see the empty bound is the dotted line and the solid line is in our new bound. So you see the empty bound is lying somewhere here, okay? Whereas the ideal line is this. You see how loose this empty bound is. Whereas our bound is lying somewhere here, very close. And this line almost on top of this dotted line, you see? So this shows that this new stronger bound really captures the time that you would like to estimate. Okay, so this is almost on top of this for n equal to 2 and for n equal to 8 and 14. This is almost very close to the ideal line. Now do the opposite. You change the number of subsystem and fix the dimension like qubit. Okay, and then you change in the different subsystem. Again, you see the similar behavior. Okay, this new bound is much closer to the ideal line, whereas the empty bound is much loose. Okay, so just to show you how good this bound is. Okay, so I will now I will move on to a new notion about quantum speed limit for observable. Just to motivate a little bit, till 1990, sorry, what is this? Till 2022, just 3 years before, okay, all the research was done only for, trying to answer the question how fast the state can evolve in time, okay? So quantum speed limit for state, okay? Now, if you recall your textbook, quantum mechanics course, you know that in quantum mechanics, one kind of picture. One is Schrodinger picture and other is Heisenberg picture. Okay. In Schrodinger picture, states evolve in time and observables don't evolve. In Heisenberg picture, the opposite happens. So states don't change, but observables evolve in time. Okay. And then a natural question comes to mind is what happens to the speed limit in the Heisenberg picture? And interestingly, or maybe surprisingly, this simple question was not answered till 2022. Okay, so myself and one of my students will try to address this question. Of course, this question was there in my mind for many years, but I never, really got time to sit down and think deeply. So I suggested to one of my students during his PhD time. So he looked into this and we did interesting thing here. So just to motivate students, simple questions at textbook level still can make interesting research directions. Okay, so we ask the question: how fast your observable evolves in time? Because if you want to do something in the Heisenberg picture, obviously this will come to your mind, right? So that's what we do here. Okay. And then we realize that this speed limit for observable, because if you get an answer to this question, you can have the speed limit for observable, and this can have a lot of applications in many body physics, in condensed matter system and many other things. So, like in complex quantum systems, one of the pressing questions is to understand the universal operator growth hypothesis. So, at time t equal to 0, you have a simple observable, and as time evolves, that becomes more and more complex, more complicated. Okay. Uh, so the observable of the system which may be represented by operator, tend to grow over time, and that is how it's called how fast your observable becomes more complex and more more complicated. Okay, so the QSL for observable will tell you the maximum rate of evolution of the average of an observable for a given quantum system due to dynamical evolution, and that will establish a time limit on the minimum evolution time that is necessary to evolve between different average quantities of a observable of a quantum system. And if you are interested, you can look at this paper in 2022. Okay, so what to do? You start with your familiar Heisenberg equation of motion, that IH by dO by dt equal to OH commutator, and then you use the Robertson uncertainty relation. Then you can use the inequality that looks like this. Then if you integrate over time, then you get the t greater than equal to h bar by 2 delta h 0 to t and this quantity. Okay, and this whole thing we call as TQSL for observable. Okay, and this t greater than TQSL is our new limit for observable. Okay, and 2 years later, again we did find the stronger speed limit for observable using our relation with Makoni, and that looks like this: that t greater than h bar by 2 delta h integral 0 to t. Same thing, but there is extra factor sitting here due to those extra terms sitting in the stronger uncertainty relation. Okay, and because this eta t is less than 1, this makes greater than 1. That is how this whole thing is greater than this quantity, which is something we found earlier. Okay, so that is the reason this is called stronger quantum speed limit for observable. And this is, if you are again interested, you can look at this paper. Okay, so now I will tell you 2 applications of these ideas. One is quantum battery and other is quantum algorithm. Okay, so quantum battery is a emerging direction proposed by Ellis and Fans, basically a microscopic energy storage device. And over the last several years, many theoretical work have been going on, and people are trying to exploit the novel idea of quantum battery and how to enhance its features using non-classical, resource like coherence or entanglement or other correlations. And the hope is that quantum battery can easily outperform classical battery because of several quantum advantages you see there. And quantum battery consider many quantum systems with several degrees of freedom in which you can deposit energy or start work from it. So in quantum battery, what you have is a system Hamiltonian, you have battery Hamiltonian HB, and then you can charge it by driving field, which is SC. So total Hamiltonian of the whole system is HB plus SC. And then the amount of extractable energy from the quantum system by unitary operator is given by this expression, which is often called ergotropy of a quantum battery. So you look at the average of the battery Hamiltonian at time t minus the average of the battery Hamiltonian initial state. So the difference give you the ergotropy. And quantum battery has a lot of application again in quantum computing, because quantum batteries may provide efficient and quick energy storage in future, and nanotechnology, because quantum battery again you can use in nano devices where traditional energy storage could be impractical due to size and efficiency constraint. And also could have application in advanced electronics, because as miniaturing continues, quantum battery could play a role in powering smaller and more efficient electronic devices with higher energy and faster charging capability. So a lot of opportunity, a lot of potentials are there. But then again, like building a full-scale quantum computer, this is also quite challenging, because we know that quantum systems are very sensitive to external noise that will lead to decoherence, and that will again disrupt the quantum system or quantum state that you need to store your energy efficiently. Okay, and again, if you talk about scalability, again same issue. Creating quantum battery on large scale again remains a challenge, but nevertheless, the ideas are very promising, and a lot of people are actually working on this. Okay, so I will give you one example how where you can actually estimate the charging time using our QSL for observable. Okay, So here I want to show you the minimum charging time of quantum battery. So previous bounds for quantum battery were based on the extinguishability of initial final state. But what you will do is you will use the speed limit for observable and stronger speed limit for observable. So that will tell you that our bound is based on the difference of the initial isotopy and final isotopy of quantum battery. And then you can show that our bound can easily outperform previous known bounds. Okay, so you consider entangled quantum battery, a 2-qubit cell coupled to two-level system like HB plus SC plus MH interaction, and your HB looks like this, and SC looks like this. H interaction, all sigma, X sigma, S sigma, Y sigma, and all such things. Okay. Now, what you do is you identify empty and full. Empty means you start from the initial state, no charging. Full means you go to up, that is charging. Okay. And they have this energy. Now, again, don't worry about too much details. So I will just show you how good this bound is. Okay. So if you plot the TQSL due to stronger bound and the TQSL, then I so sorry. What you do is so you hit T was a T QSL. So this ideal line is something like this, but our stronger one exactly sit top of that. Okay, and this is the TQSL bound obtained in 2022, and this is new bound in 2024. Okay, and this is the long time behavior. So even long time behavior also predict exactly matches with the stronger bound. So this is the beauty of the stronger quantum speed limit for state and observable. Okay, now I will go to application of quantum speed limit in quantum computing. In quantum computing, already you know that is going to change, our future ability in terms of computing abilities and other things. So one of the in early days we have, people have been asking the following question: that whether what really gives the power to quantum computer? Is it just superposition principle or is it entanglement? So these kind of questions were, being asked in late 90s and 2000, early 2000. So, so in that context, we had done something, but I'm not going to tell you, how entanglement actually helps. But we have shown that in case of Grover's algorithm, you need entanglement to have this speed up. Okay. So, but in today's talk, what I will do is I will try to use the geometric idea or quantum speed limit idea, and I will use those ideas in Grover's algorithm and tell you that how you can find a mark item in this many steps. Okay, which gives a quadratic speed up compared to classical search algorithm. In the same paper, we have also studied the role of entanglement. So we have shown that even though entanglement is present throughout the computation, the change of entanglement per iteration is exponentially small for large database. That means entanglement consumption is there, but you don't need too much entanglement. Okay, so but that is another story. Okay. Okay, so let me give you the brief background to Grover's algorithm. So what you do here is you want to find a mark item, okay, from n entries, and in language of quantum oracle, basically you're given an unknown binary function fx that returns 1 for unique target value, like x equal to y and 0 otherwise. Okay, and x can take 0 to 2 to the power n minus 1. Okay, and n is 2 to the power n, and your goal is to find that particular y which will satisfy the condition f of y equal to 1. So what you do the following thing, that you map all the n entries onto n capital N orthogonal state of the n qubit system. Then quantum mechanically the problem becomes basically trying to maximize the overlap between the initial state of n qubit and the target state. So this, as I said, this is equivalent to maximize the probability of finding the desired item upon measurement at the end. Okay. So the way to proceed is initially choose your state to be 0, 0, 0, then apply Hadamard gate on all n qubit state, and you create a superposition of equal superposition of all possible bit strings. Okay, the state at time t equal to 0 will look like something like this. Okay, This is basically equal superposition of all orthonormal bit strings. Okay. Now in Grover search algorithm, what you do is you design your Grover operator, which is basically minus I0 and IY, and you repeatedly use this to find the mark item. What is I0? I0 is basically this identity minus twice projector I0, and IY is identity minus twice projector IYY. Okay. So if you keep on applying this k times, what happens is your Grover operator corresponds to small rotation in two-dimensional subspace spanned by initial state and target state. Okay. And each such rotation requires a single oracle call, and you can show with a little algebra that after k iteration of Grover operator, your NQ state evolves to psi k, basically cos theta k, divided by this factor times the sum over x not equal to y plus sin theta k times this y. Okay, so basically this whole thing like state which is orthogonal to y. So this psi k basically cos theta k, say you can call that y bar plus sin theta k y. Okay, and y and this y bar they're orthogonal. Okay, now theta k basically you can figure out twice k plus 1 times theta 0, and theta 0 basically sin theta 0. I mean, theta 0 defines the relation, so theta 0 basically sin inverse of this 1 over square root of n. Okay, and then you will see that this search process is complete when you reach the target state, and that can happen for theta k equal pi by 2, and that will take basically this many iterations of Grover operator. So that is the main reason why you need this quadratic number of steps. Okay. Now, what I want to tell you is that you can understand this in a geometric manner using the notion of distance and speed. Okay. One thing I notice here is that in this case, the states are evolving, are changing in a kind of discrete manner, not continuous manner. There is no actual time, but you can imagine your number of iteration k as a analogous to time parameter. You can do you can find the speed, everything you can do, treating k as a continuous variable, but for simplicity, I will give you a different argument to arrive the same result. Okay. So what you do is you look at the distance between the initial and the final state. Okay. And then you look at the distance that your quantum computer moves in one application of Grover operator. Okay. Then what you do is you divide total distance by the distance moved in one iteration. Okay. So this ratio will give basically the number of steps you need to reach your final state. That is simple idea. Okay. So what you do, you take the definition of distance between two quantum states like psi1, psi2. As I said in the beginning, this is basically this is 4 into 1 minus psi1, psi2 mod square overlap. And then choose your psi1 to be the initial state, psi0, this initial state, and psi2 is the final state, psi0. And obviously, if you look at this overlap, this quantity will be cos theta 0. Okay. Now again, in a very simple manner, you can find out what is the distance between the psi0 and psi1. Psi1 is just the state up to one iteration. Okay. So psi1 from here you can see psi1 is basically cos theta 1. The whole thing I call y bar plus sin theta 1 y. Okay. From here you can find out what is distance between psi0 and psi1. That turns out to be sin 2 theta 0. Now, if you take the ratio total distance divided by the distance in one iteration, that will give you the number of steps you need to find the target state. So this ratio basically scales like goes like square root of n by 2, so that you can say for large database this is basically of the order of square root of n. So that is the reason why your Grover quantum search algorithm takes square root of n number of steps. And this is very beautiful geometrical notion going on here, because what happens is in a more if one understand more deeply, you can check. I'm not going to tell in detail, but you can check that this quantum state of the n qubit actually moves along the shortest path at each iteration. Okay, of course, given any two endpoint, there are infinite number of paths you can connect, but there is only one shortest path. And Grover operator is designed in such a clever manner, okay, that each iteration takes the quantum computer along the shortest path. So it moves along shortest path, just reaches the target state at least possible number of iterations, that is basically square root of n. Okay. So so some of you, if you're interested, you can also check that if a quantum system evolves along geodesic, it satisfies the so-called parallel transport condition. Parallel transport condition basically tells you the following, that the change in state at each instant of time is orthogonal to the state itself. That means if you take the, imagine that it is a continuous time evolution. Then what will happen is, if your state changes in time, then d psi by dt will be orthogonal to psi of t. So that is basically the parallel transport condition. Some of you, I don't know if you are familiar with so-called theory of geometric phases or Berry phases. This notion appears very naturally there, but even then, very simple condition we can check also. Okay, so you can check yourself that if you treat the number of iteration as a continuous parameter, and if you take derivative of psi k with respect to k, and take the overlap of psi k with d psi k by dk, that will be exactly 0. Okay, that means it actually satisfies parallel transport condition. So that is the beauty of this Grover's algorithm, and that tells you why no other algorithm also can do better than this. Okay, this is the optimal thing you can do. Interestingly, historically, this result, the study of role of entanglement in quantum search we did in 2000 probably, but this geometrical idea was again it was there in my mind many years before, but we wrote this, and this was published in Journal of Indian Institute of Science, Bangalore in 2009. This issue, if you're interested, you can look at this article. So I'm happy that I'm talking this, in IISc, this Qiskit event. Okay, so here is virtual way of looking at this. What is going on here? So you start from initial state, you want to reach here. So at each iteration, it goes along a shortest path. Okay, shortest path. But there could be infinite number of paths connecting these two endpoints. Okay, so that is as I said, that the beauty of the Grover's algorithm, that it designed in such a manner that it drives the system along the shortest path. Okay. Okay, so you can ask the question: can you do something for all quantum computing paradigm or algorithm? The answer is no, because it's not always the case that you can move the system along shortest path. So quantum field limit provides theoretical minimum time for quantum process. Directly applying the limit to predict exact amount of time in complex algorithm is quite challenging, because actual execution time may depend on implementation details, hardware limitations, or error correction overhead, and so on. But what you can do is you can use QSL for understanding theoretical bounds and guiding development of faster quantum algorithm, and nevertheless, they are huge, but you cannot always straightforwardly use this for to predict exact runtime of specific algorithm. In case of a Grover's algorithm, it so happens the beautiful comes out, but in other cases it's not that easy. Okay. So QSL can serve as a benchmarking or benchmark indicating the ultimate speed achievable under ideal quantum control or quantum evolution conditions. Okay, now I will try to summarize what I said. So quantum field limit first state plays an important role in quantum computing, quantum information, quantum control, quantum thermodynamics, and many other directions. I tried to give an overview of the quantum field limit starting from empty bound. Then I proved also stronger field limit for arbitrary evolution of quantum state. Then I show that this empty bound is a special case of our new bound. And also I proved the quantum field limit for general observable. And we also proved stronger quantum field limit And we used that to determine the minimum charging time, and we found that this exactly matches with the charging time perfectly, okay? And we can also use the geometric idea to estimate the runtime in Grover's algorithm. And then I also tried to highlight that in this case, it comes out very naturally, very beautifully, but in all other cases may not be that easy, okay? So that's all I wanted to tell you, and thank you for your attention, and continue to explore unexplored. Thank you.
Thank you, Professor Arun, for that wonderful and thought provoking session. We really appreciate the clarity and vision you brought to such a deep topic. Your perspective on the theoretical foundations guiding the future of quantum computing was incredibly inspiring. We're excited to take these insights forward in our own research and discussions.
Thank you very much. Thank you very much. Okay. Any question or?
Uh, no, sir.
Okay. Okay. Fine. Thank you very much. So if anyone has any question, or always contact me over email or okay. Okay. Thank you. So we'll stop here.
So for the next talk, we have Dr. Nathan Ernest Noble. So Dr. Nathan is a quantum algorithm engineer and team lead at IBM Quantum, where he and his team work to ensure users get the most from the IBM Quantum platform and develops tools and methods to advance near-term quantum algorithms. During his PhD in physics at the University of Chicago, Ernest Noble specialized in quantum hardware design, culminating in the creation of a heavy fluxonium qubit, which had strong protection from environment noise and development of novel superconductivity gates schemes borrowed from atomic systems. In his personal time, Ernest Noble is deeply committed to science communication, education, and outreach. He also enjoys playing chess, theater, and macro photography. With that, the stage is yours, Nate.
Awesome. Thank you very much for the kind introduction, Debarthi, and good to see you again. So I see from Sandeepan a request for 5 to 10 minutes. I will maybe take the initial part a little bit slow for you, Sandeep, so you can go get a bathroom break or whatever it is that you need. But sorry, just for interest of time, I do need to start. So let me go ahead and share my screen. Can you confirm that you're seeing the PowerPoint presentation?
Yes, is it visible?
Awesome. Great. Hello, everyone. So thank you again, Debarthi, for the kind introduction. As Debarthi had mentioned, my name is Nate Ernest Noble. I'm working at IBM. I've been here for about 7 years. I come from a background in quantum hardware. She had mentioned sort of designing superconducting qubits. It was quite a bit of fun and a lot of interesting things to look into. Since I've joined IBM, I sort of shifted my focus from research on the design of the hardware and more in research into the use of the hardware. What that's led to my personal background is a little just a deep dive in compilation methods and how you might use sort of pulse level control in a way that is amenable to a general audience. So not what I'll be talking about today, but I'm more than happy to answer questions on that should anyone from the audience be interested in such things. For my talk today, thank you. For my talk today, I'm going to be giving an overview on the Qiskit add-ons and specifically doing a demonstration of our AQC add-on, Approximate Quantum Compiler add-on. For my talk style, I love it when people interrupt me, frankly. So don't hesitate, unmute yourself. Feel free to speak up, ask questions, post them in the chat. I have the chat on my view here to sort of see it and make comments throughout. But I think these things end up being a lot of fun when it turns into a lively discussion. So with that said, I will go ahead and start. To start off, I think most everyone here is likely familiar with the Qiskit ecosystem, but to really frame what our add-ons are, I think it's useful to think about what sits around the add-ons. So this here is the sort of stack, is we like to see it. As you sort of start off at the bottom, it gets closer to being really about that hardware design and things that I sort of originated in the field for myself. But then as you move up, it starts to try and abstract away some of those details. So at the very bottom, we have the quantum chip itself, and that chip has a lot of things associated with it in order to actually do the computation. So there's classical control electronics and other things that interface very closely with the quantum chip itself. Just for sake of interest, the chip generally sits down here at the very bottom and can be about the size of your thumbnail, actually. So it's quite small. But then, as you can see, there's a lot of sort of things that go along with this chip. So these here are microwave control lines that you then have to put filtering on. And all of this stuff up here is ultimately to connect to classical control electronics that are sitting out at room temperature. This is one of those areas where things are developing rapidly, and what's true today may not necessarily be true next year or in the near future. What sits very close to this is our Qiskit runtime. So we design Qiskit runtime to run sort of optimally with our quantum systems. And what's important about that is that we can implement a variety of error mitigation protocols or things like this with good efficiency and utilizing this QPU sort of effectively. What sits right next to that and is rather critical is just the HPC environment that we have, so CPUs or GPUs. So we have this notion of Qiskit serverless that actually leverages some of this, and this is going to become more critical as we actually start to try and march towards this notion of quantum advantage that is persistent. Is ultimately to really get something that outperforms classical computers, you're going to need to use the best tools both for quantum and classical, and that's really where this HPC environment will become important. Then what sits between sort of the compute power of our stack and the actual development software that most of you will interface with is this notion of Qiskit serverless. So Qiskit serverless is a way in which you can submit jobs to our backend while also getting benefits of HPC systems. So if you like to create parallel threads and spin up multiple things, then Qiskit serverless is your way to go. The most obvious benefit to Qiskit serverless is what I like to refer to as the close your laptop benefit, in that if you are just coding without serverless and doing it through Jupyter Notebook or things like this, you have to ensure that your laptop maintains connection with the system. And particularly, say, if you're doing something like variational quantum algorithms where you have a lot of back and forth loops between your laptop and the system, and if you close your laptop, it just creates problems with that. But then as we start to march up, we get into Qiskit SDK. So this is our core component of Qiskit. It is what was originally known, say, as Qiskit Terra, and now we just call it Qiskit Core. This really is the framework that allows us to do circuit generation, circuit translation, Hamiltonian generation. We have a circuit library. There are a lot of things that have the name Qiskit tagged on with it, but don't necessarily fit into this core component of Qiskit. What we'll be talking about today is the Qiskit add-ons. There's a few of them, and we'll also be releasing some in the near future. And then something that's recently been released that in the past year, at least, that's actually quite effective is our transpiler service. So when you submit jobs to our backends, you have to sort of submit it with an ISA accepted circuit type, and the transpiler service helps you do that with AI support alongside. Qiskit SDK also has some translation passes inside. This is something to supplement that. Yes, so the question on the chat is, do Qiskit dev tools come with pip installed with Qiskit? So when you do pip install Qiskit, what it does is installs this specific package right here. If you want to install the transpilation service or the add-ons or the Qiskit code assistant, that requires doing pip installation on other things. So for today's talk with the add-ons, if you're going to want to use that, you'll have to pip install each one of the add-ons. There's another question of Qiskit Air. So Qiskit Air sort of sits separately from this. There is a sort of state vector simulation that I believe, I would need to double check, but sits in Qiskit SDK. However, that's going to be a rather inefficient simulator. It works nicely in that you can just run it for 5 qubits. It's something that works well, but once you start to try and run things at larger scale, you're going to want some of the efficiencies that come from Qiskit Air. I would need to double check, but I think for Qiskit Air, you also have to actually do a specific pip installation of it specifically, rather than it being installed with the Qiskit SDK package. So these dev tools here are really ideal when you are somebody who is fairly familiar with the details of quantum applications, quantum circuits, quantum information. Is it allows you in a granular sense to start working on building those things up from scratch. For people who are coming from a different field or who are just starting off in quantum computing, the Qiskit functions catalog can be a useful abstraction. What this starts to do is some of the details of how you get the problem of interest that you want to study onto a quantum computer can be abstracted away, and we'll talk about what the Qiskit patterns are, and that sort of helps you. But what's nice about these functions is that it handles some of the lower level details of how you generate your circuits and how you actually submit the jobs and all those things, so that you don't necessarily need to worry about those as you say are trying to start off from an application-oriented perspective. So if you're somebody who comes from optimization or chemistry and you want to do a max cut of a graph or find the ground state energy of some molecule, you can build that up, and it's not too difficult actually from the sort of components sitting in this development tools. But the application functions in particular help abstract away some of those details. So to help actually understand how the Qiskit application functions or whatnot work, and generally any sort of quantum workflow, we have this framework that we like to call the Qiskit pattern. So generally, this is how you can break any quantum workflow down when it comes to running it on a quantum system. The very first step that you're going to have is that you're going to need to map your problem to a set of sort of circuits and observables. So generally, if you're coming from chemistry, you have some Hamiltonian say that you wish to describe what your molecule is, and maybe you even have a way of understanding how to represent the unitary that allows you to determine the ground state energy of your molecule in this case. But you need to actually translate that into something that can be run on the quantum system. So what that ultimately comes to is that you need to develop circuits and observables. So an observable is effectively a Hamiltonian, but to run it on our quantum systems, you just need to represent it in a Pauli representations, because that's the easy way in which you can actually start to take measurements on the systems. And then you'll also need to generate the associated circuits that you sort of will use to approximate that observable. So then now answering another question, how Qiskit transpiler passes optimized circuit compared to compiler optimization like LLVM for C++? So that is a really, really good question, actually. So the LLVM's details, just coming back to this plot here, are really going to be sitting at this quantum computer level. The reason being is that they are the things that are needed to interface with the classical control electronics in an efficient manner. Whereas the Qiskit transpiler is going to be sitting up here. So there are sort of very interesting questions that you can think about in terms of how do you get the same level of control that an LLVM has with some abstraction that you have in the Qiskit transpiler service. The way that these things connect is ultimately your job is scheduled, and there are some details in terms of how you can handle that. But the transpilation passes largely are focusing at a more abstracted level than something like the LLVMs, in that they're going to be taking a look at the gates that you have and then optimizing how those gates can be implemented through a variety of different passes, and will not necessarily be fine-tuning the optimization of a particular scheduling. There are some details that you have in control of that, but a bit beyond the scope of today's conversation. So coming back, very first step in the pattern is that you map stuff, and then you're going to be getting to this thing of the transpiler optimization pass. Really, that is taking this ISA circuit or observable, say, and trying to optimize those at that more abstracted level of the quantum circuit. And there's a variety of things that go into that, and happy to answer more specific questions on that. Of course, Kapil, happy to answer. So once you've gotten your circuit to be sort of optimized in terms of, say, circuit depth or gate count, and minimizing the number of observables that you wish to measure, then that's when you'll actually go and run it on the system. So this is where we have our Qiskit runtime primitives. In this, we have two different types of primitives. The most primitive is sampling, in that you just purely wish to measure from your quantum system and do things with the bit strings that you measure. And then the slightly less primitive, but still something that is a very common workflow, is this notion of measuring an expectation value. So we have our estimator primitive for that. Now, you can build your own estimator primitive from the sampler primitive that we have. And in some cases, there's benefits to doing so, but that estimator primitive allows you to abstract away some of the details so that you need not worry about it. So to give you an example of what that might be, and comes to this notion of how you might optimize your circuit as well. Let's say that you have a variety of observables that you wish to measure. Say it's very common in QAOA type circuits where you just wish to measure a weight 1 Z observable on a variety of different qubits. When you're wanting to do that, well, Z observables commute with each other. And so ultimately, you don't actually need to worry about running multiple circuits for each observable that you wish to measure in the case of measuring different Z terms. And so what the estimator primitive handles for you there is that it will run the circuit that you provide it once, and then sort of do the post-processing to calculate all the different observable values based on that one run that you did. Now, sometimes you provide observables that don't necessarily commute, and in that case, what you have to do is change the basis gate of measurement that you do at the end of your circuit, and the estimator primitive will handle that for you. Now, there may be reasons that the estimator primitive sort of abstracts away certain details that you need access to for your particular workflow, and then that's a situation where you might want to handle using the sampler primitive instead. And then the very last step here is that very rarely is it that you are just needing the bit strings that come out from the quantum system to answer the question of interest that you provided in the first place. Generally, you have to do some form of manipulation and post-processing on those bit strings to generate the answer that you wish to have. So say in the case of measuring the ground state energy of some molecule, what that will look like is that you're measuring a variety of different Pauli observable terms, and then you'll have coefficients in front of them, and then you add them up, and then that gives you your sense of energy. And so some of those steps then need to be handled in this post-processing step. In addition, the post-processing step can actually be a great way to improve the quality of the circuits that you're ultimately running on your system. So as people are well aware, I'm sure, today's quantum computers are noisy and have imperfections associated with them. Error mitigation that you use in the primitives is one way to handle those imperfections, but another thing that you can start to do is, say, run You can do error detection approaches where you actually make measurements in the middle of your circuit to detect errors that have happened. And when you do that, then you can filter out the things that have bad errors through this notion of doing post-processing. This isn't quite error correction because error correction would detect that error and then in real time do some feed-forward operations and fix it. Whereas in error detection, you are ultimately taking the measurements and using that as a way to filter out counts that you know there are issues with. And that's one example of a way in which you can do post-processing, and there's a variety of different things. So one question, if I want to do some post-processing in classical computing, like running a deep learning algorithm and passing the data during test, how does the data coming from the QC look like? So this may be something that's good for you to unmute and clarify if I don't answer your question appropriately. But the data from the quantum system is ultimately going to be coming in the forms of measuring different bit strings. So you either measure your qubit as being 0 or 1, and then that you'll do that, say, on a variety of different bit strings. Or on a variety of different qubits, which then gives you sort of a given bit string with a given count that you have. And then now you can manipulate and use that in a variety of different ways. So it is possible that you could take those bit strings and feed them into deep learning algorithms to achieve whatever goal it is that you may have. So I do know that some folks like to do research on say using machine learning generally. I don't know if it's deep learning specifically, but using that to do error mitigation protocols. I think there's interesting research in that direction. It's not the direction that IBM takes for nuances on how you verify the output. Machine learning algorithms often aren't well understood in terms of specifically what they're doing. So it's not a common thing for us at IBM, at least, to use it for error mitigation protocols. But I do know it's a very rich area of research. And then there's other things that you can also use in that vein. So ket 0 would look like bit 0. Yeah, so if you had an example where you would care about ket 0, say, is so directly to your question, yes, like ket 0 would just be your bit string of all zeros, and you would measure that in some way. And that bit string might actually be, so one of the quantum machine learning algorithms is doing kernel estimation with our systems. And that is actually one way in which you want to in the original implementation from IBM is you just measure the projector 0 effectively. So ket 0, how many of your qubits are in that? And then that helps you sort of estimate the kernel for some wave function that you run on the system. And that wave function in some way connects to data that you've encoded into the circuit and allows you to do a form of kernel estimation. And then you would do post-processing on that. Awesome, of course. So then now moving into the add-ons, we have a variety of different add-ons. Here I've shown 5. We're actually going to be releasing some in our upcoming flagship event, the Quantum Developer Conference. But staying focused on these, they're broken down into sort of different parts of the Qiskit pattern. Now, this is nice because what it allows you to do is that you can start grabbing and using modular, which ends up being one of the things that I'll just plug is that we, namely a person on my team, Renajit and DeBarthy, this past summer, did a really awesome project where they combined OBP and circuit cutting and showed that through the combination here, you can actually make this circuit cutting add-on a bit more powerful than it would have been otherwise. But so we have a few different ones, and I just sort of want to walk through it. So to start off, we have this notion of MPF, which is our multi-product formulas. The way that this works is that ultimately you want to do some time evolution of some Hamiltonian that you are interested in. Generally speaking, those circuits can be quite deep and difficult to actually execute successfully on the hardware. And so you can use this notion of multi-product formulas, which creates multiple circuits with sort of shallower depths that then ultimately allow you to get a better answer. So you start off, and I'll get into the details in just a second of how this works, but you take your original sort of time evolution circuit that you have, you do some different product formulas, which are a way to estimate that time evolution. And then from that, you are now going to have multiple multiple circuits and the observable that you wish to measure. You'll feed that through the rest of the things, and then you'll do this notion of post-processing. Now, computational trade-offs here. This is actually one of the add-on methods that scales nicely in the sense that you are going to generate a small number of sort of circuits in your overhead, as well as a few it's not going to be too much computation for your classical compute side. The difficulty of this is that it's not necessarily generally applicable. It's going to be highly relevant for sort of Trotter formulation type problems, but say for estimation of a ground state energy of a molecule, it may not necessarily be as relevant. Furthermore, it's a little bit tricky in that you need to tune the parameters carefully. It's not obvious that you can sort of simply take the default settings, run this, and expect it to work well. Now, how does this ultimately work is that we have, say, some observable rho of t here, which is taking our initial state and then evolving it for some time with a given Hamiltonian, and that'll produce this sort of circuit that you have here. Now, generally speaking, this circuit might be too deep, so what we're going to do is we can approximate this rho of t with this notion of multi-product formulas. Now, we can take sort of a first-order product formula, which is going to have the deep or the most shallow circuit, and then you can also begin to take higher-order approximations. So then now what happens is that you will take the first order will have a much shallower depth, and then second order will have a slightly larger depth, and then third order even more. And then now through hopefully having the shallower depth circuits that you can sort of expect the output of your quantum system to be better, then you can sort of overall improve the estimation of your time evolution. So now what this will require is that you sort of choose the number of Trotter steps that you wish to run. You're going to generate these new sort of product formula circuits, and this is one of those tune parameters that you can tune. And then you ultimately now need to think about what's the right way to add those up, and then you do the post-processing. So the adding them up is where you basically are just doing some linear system of equations. Then moving on to another add-on is our operator backpropagation. So the operator backpropagation is a tool that will allow you to ultimately take, what's nice about this is that it can be applied to any general circuit, generally speaking. And what you can do is take the circuit and observables that you're interested in measuring. It can only be applied to observable problems, so sampling type problems can't necessarily use OBP, somewhat built into the name. But you will take your original circuit, you will transpile it through some of the work that DeBarthy helped us out with this summer. Actually, we realized that there's benefits in the order of doing this. So transpilation first, I believe, was the way that was sort of more efficient and gave better circuit depths. DeBarthy, do keep me honest on that one. But then now you're going to go through this notion of operator backpropagation. Basically, what operator backpropagation is doing is it's taking the Heisenberg versus Schrodinger picture of quantum mechanics, in that rather than evolving some unitary, what you could think about is updating the observable that you wish to measure. Now, so we'll get into the details of how that works, but you create sort of a new set of observables that you wish to measure. You'll run this through the estimator primitive and then do some post-processing after the fact. So we have another question here. How does Qiskit translate Python code into executable functions for quantum hardware? Is this translation process comparable to how high classical, high-level languages are compiled down to the machine code? So it's a good question, Compil. That's where I think those LLVMs that you had referenced earlier come into play. I don't know how, so I don't have strong familiarity on the classical side of these things, so I can't comment on how similar they are. But it ultimately is where the way that it works is that you'll have your Qiskit. Once you do this transpilation circuit, the final step that you do here is scheduling the circuit, which gives you, for the given gate sets that you have, particular timings of pulses and things like that. And then those details are handled sort of within the primitive code. We use our own particular intermediate representation that I don't remember what it is off the top of my head, to be honest. Chasm 3 is the common thing that we use. Though I think there's lower level details beyond Chasm 3, but then that translates how to actually tell your waveforms to generate specific things and things along those lines. But so staying focused on OBP for the second, the computational trade-offs for OBP are where there's maybe difficulty. So it's nice in that it can be used for any general observable problem that you wish to run. However, it is not necessarily going to work as effectively for any given thing, in that it will sort of, in the general sense, the number of observable terms that you have to measure as you propagate sort of grows exponentially. So this will require, in the general sense, an exponential number of quantum circuits to be run, which is obviously not sustainable. Now, you can use this to trim off a little bit of depth, but you will ultimately still be limited a bit. It is very well suited, generally speaking, to Hamiltonian simulations. That's where it sort of started off. So how does this work generally? So this is where I was talking about the notion that you are going to flip from the Schrodinger perspective to the Heisenberg perspective. Now, what that actually means in play is that you have some unitary U that you wish to run, and then you are wanting to measure some observable O. So what you'll do is you'll break it up and say that you'll have some UQ, which is the thing that you plan to run on the quantum computer, and then some UC, which is the thing that you are going to classically absorb into your observable here. So then now, how does that actually work? Is that you look, the U is the combined terms here that you wish to originally evolve. And then instead what you are going to do is update your O to be some O prime based on cutting off